All right, let's get started. Okay, I'm the second to last lecture, so hopefully your morning was sufficiently exciting that you're ready to sit through two more, and then you're done. So in response to some of the demands for more on inflation, I put a bunch of information into the notes. So I think there's like 15 or 20 more pages to the notes, big appendix on the EFT of inflation. So for those who are going to complain, it's there. You can read and go ahead and send me an email if you have questions later. So today we're going to talk about inflation, non-Gaussianity, and how we measure it in large-scale structure surveys. Okay, so we're going to start with inflation, just a lightning review of what it does and why we like it. So the basic idea starts with the possibility that the scale factor grows exponentially in time during some inflationary era. Now, the reason you would like this is because it takes things from inside the horizon to outside the horizon. So remember that our definition of horizon crossing, so we'll call the moment that a mode crosses the horizon, is the moment where the physical wave number is equal to the Hubble scale. Now, this is a constant approximately during inflation. So we'll say during inflation, this is approximately constant. And so what that means is that at earlier times, when A is much smaller than the time at horizon crossing, this number is much bigger. So when T is less than the time of horizon crossing, K over A is much bigger than H. And at T after horizon crossing, K over A is much less than H. Okay, so that accomplishes just our basic requirement that what we wanted to do was take things that are on small scales, so we make stuff on small scales, and then they stretch to be the size of the curvature scale of the universe. And then later, when the universe reheats, they can come back again. So the picture goes something like this. K is a constant. K is a constant because the universe has translation variance on these slices. So roughly speaking, during the inflationary era, AH, or 1 over AH, is going down. So the modes start as being bigger. Is this what I want? No, the modes start being bigger. This is going, got this the wrong way. I'm used to writing wavelengths. Let me get the picture right. OK, so K is a constant. And then we're comparing this. We want to compare this to A times H. So K is bigger than A times H. This is going the wrong way. Why is this not working? So I want K inside the horizon means bigger. OK, so it starts bigger. It's going like this during inflation, because this is growing exponentially. So A times H is approximately e to the H times T. It's growing. Then at some point, inflation ends. And then the universe, so this is approximately e to the HT during inflation. And then after inflation, the universe is dominated by radiation. So then H goes like 1 over A squared. So AH goes like 1 over A. And so this thing starts going down again. And so then the mode, so here, the mode is inside the horizon. And then here, the mode is inside the horizon again. But we solved the problem. Before, we were trying to generate the fluctuations out here. And now we've just extended the history of the universe to the past. We've created a new geometric region where now we can also generate them inside the horizon. So this is the picture of why it works very roughly. OK, so now to make this work, we actually need two conditions. So inflation is usually defined as two conditions. OK. OK, so the first condition is the one we talked about. So basically that we have A is approximately equal to e to the ht, where we're going to say this h is approximately a constant in the sense that we demand that the time variation of h is much less than the value of h squared. Okay, so this is the same as saying h is approximately constant. Okay, so that's the first condition. And the reason why we need that condition is what I wrote on the board. Now, the implicit second condition is right here. Okay, so we can get this kind of scale factor just from de Sitter space. Like a pure cosmological constant will also generate this, but it will never end. So the second condition is that there exists a time that we call the end of inflation. Now, for that to even make sense, what we need is a clock. Okay? Okay, so why do we need a clock? Well, in GR, there's no such thing as the time at which something ends unless there's a clock to measure it. So times are defined by clocks. So in GR, time is defined by a clock. Okay? There's no pure meaning to time if you don't know how to measure it. So what this, as a very abstract notion, we can say, well, there's some kind of operator that gets a time-dependent vacuum expectation value. Okay? And so everywhere in the universe, this operator is tracking time for me. So I can locally measure time by locally measuring this. So I'm sitting in a room. I just go and I measure, okay, I compute phi in the room. I average over my room. And then I declare that when this thing is, let's say, greater than some critical value, then inflation ends. Okay, so everyone syncs their clock in the past. So everyone was previously inside the same horizon. We all meet together. We take our clocks. We sync them together. We all have the same wristwatch. We say, OK, we're starting inflation now. We all have the same time. When your clock strikes midnight, you end inflation where you are. Okay? And now we go off, and now we're not inside the same region anymore. We all are now unable to talk to each other because we're separated by more than the horizon size. We can no longer send signals, but we synchronized our clocks in the past, and now we know how to end inflation. Now, the consequence of the second condition is that the second condition implies that there are scalar metric fluctuations. Okay, and the way to see that is we're just going to imagine that, let's say there weren't scalar metric fluctuations, but we're just going to see what happens. I'm going to define the metric this way. And now I want to ask, I introduced this thing here. Okay, this was going to be my scalar metric fluctuation. So why do I have to have this? Because of the clock. Okay, and the answer is there's no such thing as a perfect clock in quantum mechanics, right? It's impossible to measure time. So it's impossible to make a perfect clock. So we synchronized our watches in the past, but they're not going to be synchronized forever. So different places in the universe, so we start all at the same time. We synchronize our clocks in different places. And we're all going to stop when when our watch strikes 12. But there's thermal fluctuations, and so one of these clocks will get bounced a little bit further ahead, or one might be a little bit behind, just because of quantum fluctuations, or it could be thermal fluctuations, for all we know. But we definitely know there's no such thing in the quantum theory as measuring time arbitrarily accurately. So along each one of these directions, inflation lasts for a slightly different amount of time. So the expansion of the universe here is like A of t, and that's how much, from the beginning, A of t naught. But this one is going to be whatever it's supposed to be plus whatever tiny fluctuation there was of the clock. And this one here is going to be the same, but let's say it fluctuated in the opposite direction. So that means that the amount of stuff in the universe is getting diluted by different amounts in different places. And that's just what this variable is. This zeta is just a way of saying every place in the universe, they might have started with the same scale factor, but because the inflation lasts for different amounts of time, there's slightly more expansion in some places compared to others. Okay, and so this is the universal thing that describes the fluctuation. So this piece we call an adiabatic fluctuation because I can go to a gauge where all of the density fluctuations are exactly the same. They're uniform, and it's entirely the dilution, how much the physical scale factor is different from place to place, that controls the actual physical densities. So the coordinate densities are all constant, and the physical densities are just all changing in exactly the same proportion because it's entirely encoded in the metric. So this fluctuation here is often called an adiabatic mode for that reason. Now, we'll call it a scalar metric fluctuation, but this is the one that doesn't require you to put it in the metric too. You can define this in every gauge in some way. So that's why it has a name that's not the same as just writing it this way. OK, so this is the thing whose statistics we're trying to understand. Now, just to put this in a familiar picture, so you've probably seen a picture that looks like this. Maybe I'll draw a little bit steeper. And there's like a ball, and it's rolling along a hill. This is like d of phi, and this is phi. Who has never seen this picture? OK. That would be shocking if there was an answer to that, but yes, OK. So everyone's seen this picture, and there's some idea that like this is where inflation ends. OK? In this picture, the role of the clock is the fact that the fact that it's rolling slowly up here is the idea that phi is basically phi dot times t plus fluctuations. So this is like the classical motion. And I put a t here because the slow roll conditions usually mean that it evolves very close to linearly in time. So this is an example where the scalar field phi is playing the role of the clock. If I have a phi detector, I can measure time by measuring phi where I am. And then I have a physical mechanism to convert the time into ending inflation because I have a local measurement of phi via phi. It measures the local value of phi. And then it has a mechanism to decide whether or not I've hit the endpoint of inflation by defining whether my clock has run to the end here by phi end. But again, we have these fluctuations. These are the fluctuations of phi. Of our fundamental scalar phi. And these are the things that are going to give us the density fluctuations. So concretely, we can write this zeta variable as being related to, so zeta is related to the change to the amount of expansion. So there's an h in front of it because there's a relationship between the expansion of the universe and the error in time. So that's this. And then I need a delta t. So the thing that has the right units to be a time is the fluctuation in phi divided by the speed at which it's rolling. So the faster it's rolling, the smaller the fluctuations in phi change the amount of inflation. Because let's say this thing is fixed, then making it roll faster means the relationship between time and phi is decreasing. There's a 1 over phi dot in the relationship between time and phi. Yep. This is just like a convention. Like this will take some amount of work to get that. But let's see. Can I? Real time, I'm not going to get it because it probably depends on which way it's rolling and the sign of this thing. So I have to get that right. OK. So this is single field inflation. Now, in principle, you can have multiple field inflation. So in multi-field, it can be much more complicated. So you can just have the direction of the clock itself, but you can also have the end depend on other fields. So you could have like this t end could be a function of perpendicular directions. So we'll just call those phi perpendicular, right? So we imagine we imagine we can make our field space so that phi is rolling along some direction like this. We'll call it phi parallel. And then there can be all kinds of fluctuations in the perpendicular directions. And the region we define as the end of inflation can be more complicated. So this might be phi end as a vector. Like we live in some field space, and there's some surface that defines the end of inflation, but it mixes the transverse and the parallel directions. And so when this happens, then zeta itself is not uniquely determined. You need to know the relationship between the end of inflation and these extra fields. So when this happens, all we know is that zeta is some function of phi, all the phi's you have in the problem. OK, so far so good? OK, so our goal is going to be to try to understand inflation by understanding the statistics of this zeta. Because zeta is ultimately going to be the thing that changes the density fluctuations, the things we go and measure. So, OK, how many people know the de Sitter quantum fluctuation calculation reasonably well? Confident in it? OK, not a lot of hands. So I should go over it again. OK, so I'll use my time to cover that again. OK, so the intuition, so to understand what's going on, we need to understand these fluctuations of the field. Like this fluctuation here or in this direction are going to control zeta, the adiabatic fluctuation. So you can get almost all the intuition you need from a massless scalar and de Sitter. OK, so a massless scalar and de Sitter, I'm going to write the action in conformal time. So remember, when I work in conformal time, the action looks like this. OK, so this is defined so that dt is equal to d little t over a of t. You can integrate this equation to find out that tau is equal to -1 over ah, or that a of tau is equal to -1 over h tau. And tau here runs from -infinity to 0 in the slicing of de Sitter where a of t is e to the ht. Okay? This is also the concrete sense in which we solved the problem of generating the modes by creating negative time. So in the original FRW, time went to 0 in the past. So the universe started at t equals 0. And what we did was we invented t less than 0. And at t less than 0, all the cool stuff happens. We generate our fluxions there, and we pick up at t0, and we go through the normal evolution. So roughly speaking, the entire trick was just to invent t negative time. OK, so the reason I've done that is just in these variables, the action becomes easier the equations of motion in particular become easier. So a massless scalar has action. So this is the measure. There's an a to the 4th because there's an a in front of everything, not just an a cubed. But now remember, my derivatives also have to be written in terms of derivatives of x and derivatives of tau. And so I have to contract those with the metric. So I'll get a 1 over a squared for when I put derivatives. And I'll have phi prime squared minus OK, where prime is derivatives with respect to tau. And here I've contracted just with the Kronecker delta. OK, did I pick the wrong board? OK. OK, I'll go to another board. OK, so this is the action. Now we just want to find the equations of motion. OK, so that's an exercise that's not too hard. The key thing to notice is because there's a net a squared out front. And a, remember, goes like 1 over tau. So there's a net 1 over tau squared sitting in front of all of the derivatives. And so that means, so I'm going to Fourier transform the spatial coordinates into k's, and that will give me equations of motion that are phi double prime minus 2 over tau phi prime plus k squared phi equals 0. Okay, the minus 2 over tau came because there was an overall 1 over tau squared. So that I just integrated by parts. I hit 1 over tau squared, get a minus 2 and a 1 over tau. And then I multiplied the whole thing by tau squared to get rid of all the 1 over taus that were floating around. And so I'm left only with this. Now you can solve this equation so that the classical solution we're going to write as, in a very suggestive way, oops, 1 minus ik tau e to the I k tau plus. So I've chosen my two constants of integration to be k, a dagger and a, because I'm writing complex solutions. And then I need an h, and I need also a squared k. Okay, so I have cheated you here. So here I'm intentionally putting a constant that I happen to know is the right constant, and we'll see why it's the right constant. This part you can just by plugging this into Mathematica. So there's nothing particularly fancy about getting this result. It's sufficient to just solve the equations of motion. Okay, so but I did cheat you because I wrote a Hubble and I wrote a 2 over k cubed, and that's clearly a constant from the purpose of tau. So I clearly picked that for a reason. Now, the reason is going to be that my goal is going to be to promote this a dagger and this a to the creation and annihilation operators. And so I've anticipated that my goal is to make this a quantum theory. So to quantize, I'm going to promote a dagger to a hat dagger. I know this is annoying because there's not lots of A's, but these are the standard conventions to just carry everything called A. And so we'll try to keep track of the K's for that reason. And similarly, A, K will go, oh, I'm supposed to put a minus sign here. Minus thing, that goes to the operator where these obey the standard commutation relations where it's just a delta function. Okay, so the key question is, why did I pick the solution in this particular way? So first, why did I pick, I mean, obviously the classical solution has both terms. So why did I pick this term to stick in front of a dagger? Remember your, chapter 2 of Peskin or whatever book you use. I can't, did someone give an answer? Okay, and so what defines the Mankowski vacuum?
Canonical commutation relation.
So I have those, but actually I have more than one way to satisfy the canonical commutation. So that's not enough. Positive frequencies. So what I want here is I create positive frequency modes. I don't create negative energies. I create positive energies. And so the vacuum is 0 energy. So that's what I want. Okay, so this choice is where all people who say words like Bunch-Davies vacuum and why did you choose the Bunch-Davies vacuum, they get really upset. And they want you to include a linear combination of these terms. One way to understand what they're doing is they're just starting in a higher energy state. They're starting in a higher energy state than the vacuum. And specifically, if we follow these solutions backwards in time, so that if we take tau goes to minus infinity, so that k over a is much less than h, so we're inside the horizon. We would like to think that if we're on a tiny region compared to the curvature of the universe, that this should look like flat space. So our assumption is that this should look like flat space. So all arguments about the choice of the vacuum is just whether your vacuum at arbitrarily small distances inside de Sitter space should look like flat space. Now, we live in de Sitter space, and we are currently sitting in a fairly small region compared to the expansion of the universe, and it seems like flat space is a pretty good approximation. So I am not going to have a further argument about this choice. Seems pretty good, and we can test it in this room. There's not an infinite amount of energy hitting us all the time. But that is what some of these choices correspond to, an infinite amount of energy in flat space. So we don't like that. We've made this choice. Now you can check if you take this limit that these things start to look like the WKB solutions for a slowly varying frequency. So roughly speaking, your solution will go to this. I'm going to just write it out for the sake of time. In the limit tau to minus infinity, the dominant contribution comes from this term here. So I can neglect the 1 compared to those terms. I'm going to write it in a suggestive way. OK, now this is not immediately obviously the flat space mode, but you should remember that whatever our flat space frequency is, it should obey that it's equal to, in some WKB sense, our physical wavelength. This is the equation for a massless particle. But it's still varying in time. So this term here, for example, should presumably be ik times the integral over time of omega of time, like that. If I'm doing WKB, it should look something like that. And you can check that this is indeed what you would get by doing WKB. Because if you integrate this, you get a minus 1 over h from the integral. So, which is right here. OK, now this term here is also what you'd expect from WKB. It's the 1 over square root of the frequency with our appropriate factor of 2. So that's good. We have this funny factor of 1 over a to the 3/2. That's because we Fourier transformed with respect to k. And if we were in flat space, we'd Fourier transform with respect to physical momenta. And so we have an extra a floating around because we're using the wrong momenta from the point of view of a flat space person. So this limit is just reproducing flat space physics. So if you just said, there's some fancier words people use about how to impose the correct vacuum. But at the end of the day, you just said, when the mode is well inside the horizon, it should look like the WKB approximation of a flat space mode. Then you would land on this solution. Was that? Oh, sorry. Yes. Sorry. Correct. Inside the horizon. I always get inside. And intuition is long, and then k, it's backwards. Anyway, I'm sorry. Yes. Thank you for the correction. Yeah, that should be in this way. OK, other questions? OK, so now we can discover what happens in de Sitter space. We basically just reproduce flat space, which you might be unimpressed by so far. OK, so now what happens when we go to the opposite limit? So we take tau to 0. That's taking k over ah much less than Hubble. It's a super horizon mode. And if we expand our solution out, it will become h over square root of 2k to the 3/2, 1 plus 1/2 k squared tau squared, plus I k tau cubed over k tau all cubed over 3, and I still put my 1 over square root of 2k to the 3/2 plus the Hermitian conjugate. OK, I split these two terms up for a specific reason, which is that there's an I here. So you should think of this as being the two different solutions to a second-order differential equation. This term, because there's no i's, like all of these terms are related to each other, this is one classical solution, and this is another classical solution. Yep.
Sorry, what is the first term and the first parenthesis?
This.
It's inside the parenthesis.
Oh, it's just one. Sorry. OK, so tau is going to 0. So the first thing that this tells you is that if I calculate the 2-point function of phi, I can drop everything except for this first term and my a's and a daggers. And so I get that I get a 2-point function that follows this usual scale invariant answer, and then my momentum conserving delta function. OK, so this is the standard explanation for how you got quantum fluctuations, produced statistical fluctuations later. But actually, so far, I haven't done anything. I just calculated a 2-point function. I could have calculated a 2-point function at any time, even in flat space. You still get a non-zero answer. So far, you shouldn't be particularly impressed that I got a non-zero number. You'd always get a non-zero number, OK? The thing that's actually going on here that matters is this piece here, OK? This piece here is what tells you that the commutator is going to 0. It's the piece that tells you that quantum mechanics is turning off as you go outside the horizon. And so you're turning quantum into classical. Now, there's a technical way to say that, which is you can't have a non-zero commutator if you only have one real solution. The commutator is basically the real and imaginary part that don't commute with each other when you take the time derivative. So the entire job of the commutator requires two pieces. But the fact that it goes like tau cubed here is like might seem like some accident, right? Like it involved me solving some equation and Taylor expanding it, and you got this. That is actually has almost nothing to do with the solution, and literally any equation you solve had better have that the commutator has that second solution vanishes like a cubed. Okay, and the reason is really simple. The commutator of phi dot and phi at two different positions, but the same time, this has to be 0 if x is not equal to x prime, right? Like it's a space-like separated distance. So at an equal time commutator has to be 0, just on general grounds, except if they're equal. So this has to be proportional to a delta function. But we're doing GR. So this is a coordinate delta function. So coordinate delta functions are meaningless. I do a change of coordinates, I get a different answer. So I always have to put 1 over the square root of the determinant of g in front of this expression. Like that's the only diff invariant answer that I can write down that has the right properties to obey causality, that modes that are space-like separated can't affect each other. So if we Fourier transform that expression, what that means is that in the superhorizon limit, now I can take this expression, decompose into Fourier modes. I get an expression Fourier mode by Fourier mode. I think there's supposed to be minus I here probably. Now this commutator also has the 1 over a cubed that comes from this. So now here I put 1 over a cubed, which is just the same thing as the square root of the determinant of g. And then I put my delta function. So the commutator has to go to 0, like 1 over the volume of the universe. So that means that no matter what we did, no matter what equation we thought we were going to solve here, we were going to get a tau cubed here, which is the same as 1 over a cubed. So it's just causality. Causality enforces that these two solutions. So if this solution is a constant, this solution has to go like 1 over a cubed. So what that tells us is that this answer we've got, this 2-point function, I'm going to use my prime notation here to drop the delta functions, that this has to be a classical statistical statement. it's not a quantum fluctuation because quantum fluctuations are too small. They're down by 1 over a cubed. So these fluctuations just have to be real. They have to be there. They have to be classical fields. So we've converted quantum fluctuations to classical when we go from inside the horizon to outside the horizon. In flat space, they're quantum fluctuations, just like in this room. If I measure a 2-point function at very short distances, I might get a non-zero answer, but that's because I put a detector in the room to do it. Here, I really did create these modes. They're really not quantum. I don't create them from the vacuum by doing an experiment. They really exist because they have to be classical. They can't have come from quantum mechanics. OK, does that make sense to people? OK, now the final conclusion we can take from this is that remember that I also needed this exact same property in order to explain why there's phase coherence. So remember we said that when we were looking at these temperature fluctuations in Fourier space outside the horizon, so k over a is much less than h, we said, I told you that some equation that I didn't write down would tell you the answer and that it would go like a constant plus another constant over a cubed. Okay? And now we learned that that had to be true no matter what. So the fact that this thing becomes classical and the fact that we get phase coherence, they're all the same result. They're the result that there's only one real solution to this equation that survives. The other one goes to 0. That also explains why quantum turns into classical. OK, so just putting a scalar field into sitter is doing a lot of work for us. That is now, OK, I have about a little while to tell you then how we go and test the predictions for these things. But maybe, so this is like the theory background. How are we doing so far? People feel better about their knowledge of the power spectrum? OK, whoever, OK, no. So I take that no hands, everyone doesn't feel it better. But we will proceed because we still only have so much time. OK, so we have these statistical fluctuations. And our goal is just to understand the physics of inflation from calculating the statistical properties. So I calculated the 2-point function in a free theory. If you have interactions, so if I have like something like, I don't know, I'll just write it an example like this. So I have a scalar fluctuation, and then maybe there's some power of the background field to make some interaction. Then I can generate like 3-point functions of my fluctuation by things that just look like ordinary Feynman rules. Okay, so I'm not going to go through how we actually calculate the different correlation functions, but hopefully you'll believe me that it's not hard to convert interesting dynamics during inflation to interesting statistics after inflation. And that in principle, if you open the notes and you looked at what the formulas look like, it's just standard looking formulas. It's just Feynman diagrams and Wick contractions and things you're all familiar with. So this thing will generate, so what we're going to be interested in is, for our purposes, the leading thing that we care about is going to be the 3-point function of the Fourier modes of the zeta variable, the adiabatic metric fluctuation. Now it's conventional to write this in the following form. So this thing is usually given some amplitude called f and L. Then there's a function called the bispectrum, because bi for 3 makes sense, but OK, that's what people do. And then there's a momentum conserving delta function. OK, I've intentionally not put the arrows on top of that B. OK, so the reason I didn't put arrows on top of that B is because the momentum conserving delta function tells you that there's actually all of the information about this correlation function can be reduced to the length of the 3 vectors. So specifically, momentum conservation tells you you have 3 momenta that form a closed triangle. And so instead, we can just think of this function as being a function of the shape of this triangle. So this triangle will have size. So like one thing it can do is be different. Like I can make the lengths bigger. And I could do some rotation that clearly shouldn't do anything. So normally this piece isn't very interesting either because we have these scale invariant answers. So all of the really non-trivial information about inflation is usually included in the cross ratios of the lengths. So we can usually define the triangle something like this. I'll define this length to be 1, or I can take k1, and then I'll just be interested, and I'll divide out every side by k1. Sorry, these are the lengths. I went backwards for some reason. OK, so I have these three things here. And then I can make this function b is just equal to what I'll call a function of these two variables. So where x2 is this ratio and x3 is the other ratio. OK, so all of the dynamical information about b is encoded in how it depends on the cross ratios. And then there's some overall 1 over k to the 6, k1 to the 6 dependence that comes out. So if you want to put general k back, this thing goes like 1. So we can write it this way. B of k1, k2, and k3 is just 1 over k1 to the 6th, b of 1, x2, and x3, assuming scale invariance. So this is scale invariance, which is, as far as we know, a pretty good symmetry. So now it's this function that contains the dynamical information about inflation. So there's this thing is set by symmetries, but this thing is the thing that depends on the details of the theory. Normally, this is defined in terms of a thing called a shape function. So the shape function is there to weight this bispectrum by which modes have the most information. So specifically, the signal to noise, if you just went and measured a 3-point function. So you took different triangles on the sky, and you just added them all up, and you weighted them by b. So I take all the Fourier modes I can find. I weight them by my bispectrum, and then I just find out my answer. The signal to noise is basically how big I expect this answer to be divided by how big I would have gotten an answer from the 2-point function of the 3-point function. So said that differently, I integrate over all possible triangles. So all possible triangles is the 3 momenta. And I'll put the overall delta function here. So this measure is what tells me that I'm just summing over triangles. There's an overall volume of the survey here I'll come back to in a second. And then I have F and L squared, bispectrum squared. So this is my signal, how big I generally expect this measurement to be if there was really a thing there. And then the 2-point function of the 3-point function of Gaussian theory is the 6-point function. And that 6-point function is just Wick contracting the 6 fields. And this factor of 6 comes from the fact that there's that many permutations. OK, so this is the signal to noise squared. You can follow this through to get the following formula. So you factor out your k1. The k1 doesn't do anything. You do an integral. That gives you the volume of the survey times k max cubed. The volume of the survey is like 1 over the smallest momentum cubed. So this is the number of modes. The number of modes I have in my survey. So as we expected, signal to noise squared, number of modes. So signal to noise square root of number of modes. Square root of number of modes is what controls our ability to measure anything. Then we have an integral over the cross ratios. There's some limits of integration here. This is not important. What's important is this factor here. So there's all these 1 over power spectra here. So the power spectra, like 1 over k cubed, that moves the k's upstairs. So there's a bunch of weightings by momenta that becomes this factor, x2 to the 4th, x3 to the 4th. So what is this thing doing? Does anyone have a guess? So let's consider what's happening when x3 goes to 0. This thing is downweighting the b's. Why is it downweighting the b's? Does anyone have a guess? So, but what happens when I squeeze the size of the triangle? Why do I get less information in those triangles? So it's actually just that there's not as many modes, right? Like I'm taking one of the momenta to 0, and as we said, the number of modes is related to the length of the momenta. So if I take a momenta that's at k min, I have one of those, right? It's the smallest momenta. So I just don't have very many modes there, so I'm losing information. So what this thing is doing is just to say the original functions might look like they blow up at k goes to 0. But it doesn't matter if they blow up as k goes to 0. They have to blow up faster than the number of modes. They have to grow faster than the error bars. And so that's what this thing is doing. So this thing is then converted, usually based on this formula, the way we usually plot the shapes of non-Gaussianity is in terms of a function called S. So S is just the b weighted by the factor that we have in front. So we just multiply that by x2, x3 squared. Okay, so this is the shape function. When people talk about different shapes, they'll make a plot of this. And the reason they put this here is because I want to downweight the parts of this function that don't have very much information. Okay, so far so good? Questions? Okay, so I'm going to just talk about 2 shapes, what the physics is of these shapes and how we measure them. Maybe just look at the notes for the plots. I put the plots in the notes so you can look at them. My ability to draw is probably not good enough for that to convey any information. So I will write functions, but I'll maybe even write what the shape function does, but you're going to be better off looking at the plots. Okay, so the first one we're going to talk about, this is the one that has some signals that are related to cosmological collider physics, which is, I hear what Raman talked about, so I will start there because maybe it's more fresh in your mind. So this is local non-Gaussianity. So local non-Gaussianity only comes from multi-field inflation. So if you ever detect local non-Gaussianity, you've confirmed there's a second field of some kind. It could be massive, but something beyond the inflaton. The usual way it's defined is in terms of the Newtonian potential, like this, F and L local, phi Gaussian squared, and all of these are vectors these are in position space. Now, I'm writing it here because that's why in zeta it's defined. So phi is equal to minus 3/5 zeta. So that is why there's a sign and a 3/5 in this expression, where I've just absorbed one of the 3/5 here, and I need to keep the other 3/5 there. But that's the convention. Okay? This kind of structure is exactly what you get in multi-field inflation if you just have the end of inflation controlled by a second totally Gaussian field. So this is a Gaussian field. Sorry, I was meant to specify phi g is Gaussian. It's a Gaussian random variable. So there's no interesting source of non-Gaussianity in the conventional sense. It's just that I took a Gaussian field and locally multiplied it by itself to make something non-Gaussian. Okay, so this is what defines local non-Gaussianity. You can't get this kind of thing in single field inflation because during inflation, the mode that fluctuates that we call the metric fluctuation, if there's only 1 degree of freedom, this would break diff invariance. Like we're not allowed to just write random powers of the metric, but if we have the metric and other fields, then we can write the other fields have some nonlinear relationship. So we convert things that don't look like metric fluctuations during inflation into things that look like metric fluctuations after inflation. So that's what's going on here. The 3-point function you just get from Wick contraction. So the 3-point function is just a bunch of products of the power spectra. So it's plus permutations. Okay, so because these things have terms that go like 1 over 1 of the k's cubed, then if we go to the shape, we can say, look, if for B local, let's just focus on the limit x3 goes to 0. There's a term that goes like 1 over x3 cubed. And so the 1 over x3 cubed is not killed by the x3 squared upstairs. And so the shape function diverges. As you take x3 to 0. So there's a ton of information in the limit where one of the momenta is vanishing compared to the other two. Now, this thing diverges, but it's really a log, right? I have to integrate up all the information. So when I do an integral over 1 over x3, I just get a log. Yep? It doesn't give you that much information. It tells you that there's enough more signal to noise at long distances that it compensates from the fact that there's fewer modes. So the net effect is that the net effect is a total signal to noise just goes like the log of the ratio of the smallest scale to the largest scale. So it's not a massive improvement, but it's a log, and logs can be helpful. Okay, so, but this fact is exactly the reason that there's a special way to look for local non-Gaussianity in galaxy surveys. So, the special strategy for looking for local non-Gaussianity is to take advantage of the fact that there's this funny correlation between the long wavelength fluctuations and the short wavelength fluctuations. So specifically, let's say I'm looking at a short density fluctuation. Well, that's some short transfer function acting on the short Newtonian potential, some small wavelength mode. But if I plug in that formula, that tells me that's short transfer function acting on some Gaussian part of the short wavelength mode. But the next thing is something that looks like a convolution. So I will get some kind of convolution between, let's say, I'm just going to put k long here, between a long wavelength phi and a short wavelength delta. So here will be the short transfer function and my phi. So I have a short delta that's being modulated by a long wavelength phi. Okay, now the key thing is that this is phi, which is never going to appear in Newtonian physics, right? Phi means nothing in Newtonian physics. So somehow the absolute value of the Newtonian potential is affecting small scale fluctuations of the density. So why is that important? So if you imagine, so here's a picture of galaxy formation. So there's a picture of galaxy formation that goes something like this. Galaxies form at some critical value of the density. So the idea is like when things cross this line, that's where I'm going to find galaxies. So if I have, let's say I have some long wavelength density fluctuation here, and then on top of that I have some short fluctuations And then I'll find galaxies in these places. So the galaxies are going to form where I cross the line. Okay, this is probably not a great picture, but you see how the long wavelength density lifts it closer to the line. So what happens is that there's more galaxies higher on delta and fewer galaxies lower on the long wavelength delta. So the density of galaxies, or the density contrast of galaxies, is proportional to the long, so here I'll just call the long wavelength density fluctuations of matter. Now, in the presence of non-Gaussianity, we get something a little bit different. So we now have the possibility, so what's happening is that the amplitude of the small scale fluctuations is proportional to the Gaussian answer times something that depends on the long wavelength Newtonian potential. So when this happens, the picture changes. So I'm going to draw, so we're going to imagine that there's some phi, let's use a color, there's some underlying phi fluctuation, which we can't locally see. Phi is locally unobservable to us. It's a meaningless variable, normally, in Newtonian physics. But it changes the amplitude of the matter fluctuations. So what happens is that, let's say in this case, where this thing is high, the variance of the fluctuations is larger. So what that means is the picture looks like this. So you just get bigger fluctuations when you're on the high points of phi than you do at the low points of phi. So what that means is that you get more galaxies, not where the density is higher, but where phi is higher. So the result is that the density of galaxies is proportional to phi, which is the same as saying it's proportional to 1 over k squared times the density. Okay, does that make sense to people? So basically what this did is it converted a 3-point function, the fact that there's a long mode modulating the amplitude of the short mode, into a linear effect, but now that linear effect has a 1 over k squared in it. So now if you go and calculate the 2-point function of galaxies, so if we plot, let's just say, the power spectrum, so remember this was our matter power spectrum. Then our galaxy power spectrum will do something like this. So this part here is the galaxy power spectrum. Okay, so you have this big effect on long distances, and we remember that all the nonlinear effects lived here. So this was like here. Let me put a different color. So this region here is where nonlinearity has lived. So this is the nonlinear region. So this is P nonlinear. So our signal is safely away from where all the nonlinearities happen. And because it looks like 1 over k squared, it's not something that comes in Newtonian physics. So this is this special signal. It looks like a violation of the equivalence principle. It lives at large scales where we can measure it. Now, you might worry about cosmic variance. So we're used to the idea that cosmic variance error bars are big out here too. And so just because the effect is big there doesn't mean that I can measure it. But there's actually a second remarkable fact, which is related to the fact that I secretly am measuring a 3-point function, even though it looks like a 2-point function, which is that if I can measure the density of matter, I can measure each Fourier mode of the density of matter, and I can measure each Fourier mode of the galaxies, then there's no cosmic variance. Because the relationship is deterministic. it says the relationship between Fourier mode by Fourier mode is that there's an F and L local and a 1 over k squared. So so what's going on here is that I don't have to pick. Cosmic variance says that I'm trying to measure a random signal. There's something random going on, and so every time I draw a random number, I can't determine if my outcome was just getting unlucky or is a true signal. But here, it's like I get to see what the seed of my random number was, right? Like if you think like I have some random number generator and then I multiply every random number by a constant, and I'm trying to figure out what that constant is, well, you'd have kind of a hard time if all you had was the number that came out. But if I know the seed number and the final number, then I just divide by them and I find out what the number that you're multiplying by. So this thing is deterministic, and what's really happening is that the actual noise is shot noise from the number of galaxies that looks something like this. This is shot noise. This is your fundamental limit on your ability to measure this effect, is the shot noise, which is just 1 over the number of galaxies. This is a short scale effect. That's what sets your ability to measure this signal. And basically, if you put all the numbers in, it's saying that even though we don't literally measure this 2-point function on small scales, that the signal to noise scales like we did. So this small scale effect here shows up in the number of galaxies and hence the amount of shot noise. So our fundamental limit is set by the number of modes, including all the short scale modes, even though we never measure any of them. They're just getting reprocessed. So we're getting the benefit of all of the number of modes right to the nonlinear scale. We're basically getting k nonlinear over k minimum as the number of modes, even though we didn't actually do our measurement over here. So physics processed those modes for us and gives us the equivalent amount of information as if we did that measurement. Okay, so how much time do I got? I got like 10 minutes. Yep.
What is the difference between galaxy pulse spectrum and matter pulse spectrum?
So this effect doesn't affect the matter, right? The entire reason this worked was because I had this picture of critical collapse that converted the size of the fluctuations into the number of galaxies.
How do you define the delta galaxy?
I count how many galaxies there are in a box, count how many galaxies are in an average box, and divide. So this is like, there. So delta galaxy is like the number density of galaxies in a specific place divided by the average number of galaxies in a specific place in the universe. It's a density contrast of galaxies. So if you go and look at like the pictures of galaxies, it has this complex web. And it has a more complex web than you'd expect from a Gaussian random field, and that's because it's doing this. It's finding the peaks of a Gaussian random field. And so the peaks of the Gaussian random field have some topological properties that people study, and that's what gives you this intricate structure of walls and domain walls, like in the distribution of galaxies.
But there are bigger galaxies and smaller galaxies. Are they contributing?
Yeah, so the way in which that shows up is a number I've been dropping. So there's some overall constant here, which we'll call b phi, that depends on the mass of galaxies. So there's some information about the galaxy formation that shows up here. So if you sit at a point where this vanishes, then you can't tell the difference. But that's something we know. It's more detailed, but the mass of the galaxy shows up in that quantity. Are there more questions? Yeah.
I also want to ask, where does the cosmic variance come from? Because in the CMB angular pulse spectrum, we know there is a maximum number of events, it's just 2L plus 1. But here is
it's the number of Fourier modes. So you have a finite sized box, right? So where did the number of modes come from? So it's literally just, this is how you calculate a power spectrum. I'll do it in 2 dimensions, right? So you take so you have a box, a finite sized box in let's say X and Y, okay? Now you take that box and you probably make a grid out of it, and you calculate the density in the grid, and then you do just a fast Fourier transform, okay? That fast Fourier transform has a discrete number of k's. Now, you organize that discrete number of k's. So one of them is the 0 mode that sits in the middle. okay? Now, the other Fourier modes start to organize something like this. So then we start going out, like it's some lattice, right? So this is our lattice of Fourier modes that we get because it's a discrete Fourier transform. Then to calculate the power spectrum, you average over like circles. So you take like regions defined by circles that have the same length. Then you average over everything inside of this circle, and that tells you the power spectrum of the scale of this length. And so you just count up how many discrete Fourier modes are in there. And so obviously there's 1 at 0 and like some small number depending on exactly how you define your bins. And then as you go out, you get something more continuous that goes like k cubed. Does that make sense? Okay. All right, so 10 minutes for equilateral. Does that sound good to people? Okay. All right, so equilateral is hard, and so it's probably appropriate that I don't spend too much time on it. But I'll just explain why you should care about equilateral and why it's hard but interesting. Okay, so equilateral non-Gaussianity is the kind of non-Gaussianity you get from interactions, even in single field inflation. So in single field inflation, you can have interactions that look like, let's say, 3 derivatives of the metric and 3 powers of zeta. Like, this is OK. It doesn't break diff invariance because there's derivatives. Okay, so we can have derivative interactions without running into trouble with diff invariance. So the derivatives give you extra powers of k upstairs. So this example gives you an equilateral bispectrum of the form. Let's see if I'm not going to worry about numbers. 1 over k1, k2, k3, k1 plus k2 plus k3 cubed. Okay. This part here is called the total energy pole. It looks like the delta function you would have got if you were trying to calculate a 0 to 3 Feynman diagram, right? We're creating fluctuations from the vacuum. If I did this calculation as an in-out calculation in flat space, it would be 0, but proportional to a delta function. In de Sitter space, it's not 0. And the way in which the delta function would have shown up shows up as a suppression by the sum of the energies of the outgoing particles. This analogy is actually more precise. If you analytically continue so that you actually hit this pole, the residue of the pole is the scattering amplitude of the associated flat space process. So there's a one-to-one correspondence between 3-point functions that look like this and interesting interactions that survive in the flat space limit in terms of the original underlying scalar. Okay, so this is particularly interesting because, the amplitude of this thing is called FNL equilateral. Okay, there's some long explanation in the notes with some pictures that I probably don't have time to draw, but roughly speaking, there's an interesting result that says FNL equilateral is less than 1 in any slow roll, anything that's weakly coupled. I'm not going to run out of space. So it's less than 1 if you have a fundamental scalar that's weakly coupled around the background. At the scale of the time evolution, which is set by the energy scale phi dot. So if your theory is weakly coupled there, you can't get FNL bigger than 1. This is roughly speaking in correspondence to all those pictures you've seen of potentials. On the other hand, there are things that are called like Dbi inflation as an example, where you can get FNL equilateral much bigger than 1. So in this case, it's just because there's a more intricate nonlinear structure to the way in which derivatives show up. But you can also get this just by exchange of heavy fields. So this was a statement about single field. So this is weakly coupled, assuming no additional field. Sometimes the way it's not weakly coupled is because I integrated out a massive scalar. So you can also generate FNL greater than 1 equilateral greater than 1 by just having more fields that UV complete the strong coupling you would have guessed from the original argument here. Okay, so if you go and look at the shape has the name equilateral for a really obvious reason, which is that it's peaked in equilateral triangles. So roughly speaking, our shape function is just going to be, what is it, x1, x2, x3 over 1 plus x2 plus x3. And this function gets most of its information from configurations where all the k's are roughly the same size. And that's why it's called equilateral, because the equilateral triangles dominate the signal to noise. Okay, now the important thing, which is related to my previous comment, is that there's no interesting behavior as one momenta goes to 0. So the signal to noise goes to 0 as, let's say, k3 goes to 0. So this scale-dependent bias effect, this thing, galaxies being proportional to the Newtonian potential, doesn't really help us here. And so we really just have to beat this thing down with modes. So our strategy, the universe doesn't help us with this one. And so roughly speaking, we just have to increase that. So we just have to measure as many modes as we possibly can. So more or less, that means taking a bunch of galaxies and calculating their 3-point function. Okay, so why galaxies? The reason is because if we just want more modes, there's more modes in the volume of a sphere than on the boundary. We've measured a lot about the CMB. We're just running out of modes. So the CMB can help us by at most a factor of 2 in improving this error bar. So we just have to go get the more modes that live in the volume of a sphere. And so that's a strategy. So this thing will, of course, get a piece that looks like, that's proportional to the underlying equilateral shape. Okay, so in principle, the information is there. The problem is that this is not the only thing that appears on the right-hand side. So I shouldn't have put proportional. I should have put includes. Sorry. So there's some, it's there, but there's also other stuff. Okay, so this other stuff is the problem. So this stuff is the problem that we need to solve if we're going to improve measurements of equilateral. Now, hopefully, I've told you that it's worth the trouble because this gives us a way to tell the canonical picture that people like with a slowly rolling scalar field, no extra degrees of freedom, from other things. Those could be exotic things, those could be extra particles. There's lots of reasons why you want to be able to split these two categories. So it's worth the trouble of trying to figure out how to get rid of all this extra stuff. Okay, so the simplest way to see the problem is to just guess what galaxy formation might do. So galaxy formation is local. It just happens, you don't need a giant box the size of the universe to know that if you're in a little region, that if there's enough density, it would form a galaxy, because dark matter doesn't move very fast. Newtonian physics works pretty well in a small room. And so the idea is that the number of galaxies in a given place is some kind of local function of the original density fluctuations. Okay, this is the sense in which people know anything about galaxy formation. Is just they say, well, that's probably what we can guess. Now, it's not even that good because we are allowed to add the tidal tensor. So there is a term that's allowed by Newtonian physics that's not purely the density. So I can also add terms that look like this. But of course, nobody told me this function is linear, right? All I know is I can Taylor expand. So I can go B1 delta B2 times delta squared, and so on. There's a thing called BG2, which is this tidal tensor squared. Okay. The problem is that all of these things generate their own bispectra, right? This generates a 3-point function. the same way that local did. And this generates a 3-point function the same way that local did. And so do all the other terms that are higher order. They all keep generating bispectra. And since I don't really know what this function is from first principles, these are just numbers that I measure in my data. So I have to marginalize over this B, all these BNs and all these new parameters. So my ability to measure F and L equilateral boils down to how well I can separate these BNs from the shape of non-Gaussianity. So I have a shape from non-Gaussianity. I have a shape from every one of these terms. And the deep worry is that all these terms look exactly the same. Now, OK, I'm not going to give you a rosy picture. That is the problem. We have not fundamentally learned how to solve this problem. This is the biggest obstacle to us. Well, this is one of the many obstacles that are stopping us from reaching the sensitivity. There's definitely enough modes in the universe to make an awesome measurement of this. It is 100% the problem, our ability to separate these different numbers. Now, the one thing I'll say is that throughout these lectures, I keep telling you, or so far today, I keep saying bispectrum. Like I've said, non-Gaussianity is equivalent to a 3-point function, more or less. I've never suggested anything different. And that's not entirely true. Like there's actually interesting information in the map that's lost when we project everything onto a 3-point function. So a lot of the hope is going to come from the fact, like let's just say this term here, delta cubed, also generates a 4-point function. And delta to the 4th generates a 5-point function. And in fact, you can show that the information in the 4-point function is more important than what it does to the bispectrum. And so your hope is that if I take all of this information and add it all up, that I actually only have these two numbers here to worry about, and that's not as bad. OK, so I'm over time. There's lots of information in the notes, so hopefully you can go and read that and learn whatever I didn't cover. OK, thanks. OK, I'm here for questions if anyone has.
Can people infer this F function by simulations?
They can't simulate galaxies very well. So they can. The key problem is that galaxies are very hard to simulate. Like they're made up of stuff. Like how much? Like what's?
You mean including baryons?
Yeah, I mean their galaxies are defined by being filled with baryons. So like the way they do surveys, they're like, we're going to take all the red galaxies, okay, and we're going to use those, okay. So a group of galaxies I use are the red ones. So if you want to say, what is this function for red galaxies, you have to be able to do a simulation that generates red galaxies in a way that's different than like blue galaxies. Like that depends on things like like it's just a huge mess. So that like it's somewhat hopeless to imagine that simulating literally everything is going to fix this function completely. Now there is hope that maybe it still helps. Like. So what I would say is that some combination. Maybe it helps us pin down these two numbers, and then these numbers we can just measure. And like some combination is not so bad.